Right now, as you're listening to this, something invisible is pulling at every ocean on Earth. It's lifting trillions of tons of water, enough to fill billions of Olympic swimming pools, and it's doing this twice a day, every day, and has been for over 4 billion years. The force behind this? A silent, glowing rock floating 384,000 kilometers away in the darkness of space. This isn't science fiction. It's the moon, and it's been controlling our planet's oceans since before the first fish ever swam, before the first tree ever grew, before anything you'd recognize as life even existed. And tonight, we're going to unravel this cosmic mystery together. But here's where it gets really strange. The moon isn't just moving water toward itself. It's also creating a bulge of water on the opposite side of Earth, the side facing away from it. How can the moon pull water toward itself while simultaneously creating a second ocean bulge on the far side of the planet? It sounds impossible, yet it's happening right now, beneath your feet. Welcome, sleepy friend, to another quiet journey with the Slappy Scientist. Whether you're here to learn, unwind, or drift into peaceful sleep, you've found the right place. Tonight's voyage will follow moonlight across the sea, exploring one of nature's most elegant mysteries, the tides. Before we begin, a quick favor. If you enjoy this cozy corner of science, give the video a like. It helps others find us. And if you'd like more starlit journeys, tap subscribe. Drop a comment telling me where you're watching from and what time it is in your world. This sleepy community stretches across every time zone, and I love seeing it. Now, settle in. Pull those blankets close like warm sea foam. Take a deep breath, and let's discover why the ocean breathes beneath the ocean's breath. What are tides, really? Picture a beach at dawn. The sky blushes pink, wind whispers, waves creep up the sand like they're stretching after a long night, peaceful, rhythmic, almost like the ocean is breathing. In, out. In, out, that's the tide. Quiet, constant, ancient. But beneath this calm ritual lies something extraordinary. Immense, invisible forces locked in a planetary dance that's been choreographed for billions of years. The star performer? Our moon. Tides are the regular rise and fall of sea levels across the globe. But they're not simple water sloshing. They're not caused by wind or passing ships. They're the result of an intricate gravitational ballet between Earth, the moon, and the sun. A cosmic push and pull that shapes the very rhythm of our planet. Twice a day, every day, the sea retreats from shore and returns. This is so regular, so dependable, that humans have tracked it for thousands of years. Ancient Chinese fishermen planned harvests by it. Medieval monks timed prayers to it. Entire cities have been built and sometimes lost because of it. But why does it happen? The gravitational dance. How the moon pulls the ocean. Imagine Earth not as a solid ball, but as a water balloon wrapped in a thin layer of land. Now picture the moon, silvery, steady, quietly determined, pulling on that balloon with its gravity. It's not a dramatic yank. It's a subtle, continuous tug. The moon's gravity pulls the ocean toward it, creating a bulge of water on the side facing the moon. That's our first high tide. Simple enough. But here's where reality shows off. There's a second bulge on the opposite side of Earth, the side facing away from the moon. Wait, what? Here's the beautiful weirdness. While the moon's gravity pulls water toward it, Earth itself also gets pulled slightly toward the moon. But the water on the far side lags behind, like a sleepy cat refusing to follow the household. This creates a second bulge, not because the moon is pulling water away, but because it's not pulling it as hard as it pulls Earth's center. Think of it this way. If you're holding 3 balloons on strings of different lengths and you start walking forward, the closest balloon follows you most eagerly. The middle one follows at a moderate pace, and the farthest one lags behind, seemingly drifting away from you. That's essentially what's happening with Earth's oceans and the moon's gravity. This gentle difference in force, what scientists call tidal force, stretches the oceans into an oval shape. One bulge faces the moon, the other faces away. It's one of those counterintuitive truths of physics that makes you pause and think, really? That's how it works? Yes, really. As Earth rotates beneath this watery distortion, different parts of the world move into and out of these bulges, experiencing high and low tides in a rhythmic pattern. It's gravity's quiet masterpiece, playing out on a planetary scale every single day. And here's what makes it even more remarkable. The moon doesn't have to touch the water. It doesn't send down invisible ropes or emit special rays. It simply exists with mass in space. And that mass, through the fundamental force of gravity, reaches across 384,000 kilometers of emptiness to move entire oceans. Its action at a distance, one of the most profound mysteries of physics, happening right before our eyes, or rather, beneath our feet. All of this happens constantly. Right now, as you lie there, the moon is pulling gently at the oceans. Somewhere, a beach is being uncovered. A boat rocks lower in its harbor. A crab decides whether it's safe to emerge from under a rock. A tide pool refills with fresh seawater. A child building a sandcastle watches the waves creep closer. The time between high tides? About 12 hours and 25 minutes. Just over half a day. That's because the moon isn't standing still. As Earth rotates, the moon is also orbiting us, moving farther along its path every hour. Each high tide is slightly delayed compared to the last, arriving about 50 minutes later each day. If you're a sailor, a fisherman, or someone who simply loves walking on the beach, you learn to live by this rhythm. You start checking tide charts the way others check weather forecasts. You plan your day around it. High tide at 6:47 a.m. today means it'll be at 7:37 a.m. tomorrow, then 8:27 a.m. the day after. It's a dance with a partner who's always running a little late. The moon is nothing if not fashionably late. Not all tides are created equal. Not every place Earth experiences the same tidal rhythm. Some places get 2 high tides and 2 low tides each day, called semi-diurnal tides. Others get only 1 of each, diurnal tides. And in a few places, tides are wildly irregular. Mixed tides, where highs and lows vary dramatically in size. It all depends on your location, coastline shape, and seafloor depth and contour. The ocean, like a cat, does what it wants. Think about it. The Atlantic coast of North America generally experiences 2 high tides and 2 low tides of roughly equal height each day. But travel to the Gulf of Mexico, and you might find only 1 high and 1 low tide daily. Head to the Pacific Northwest, and you'll encounter mixed tides where the morning high tide might reach dramatically higher than the evening high tide. Why such variety? The answer lies in a complex interplay of factors. The shape of ocean basins, the width and depth of continental shelves, the presence of islands and underwater mountain ranges. All of these features influence how tidal waves propagate through the water. Imagine pushing water in a rectangular swimming pool versus pushing it in an irregularly shaped pond with varying depths. The water would slosh differently in each case. Now scale that up to ocean-sized proportions, add Earth's rotation, factor in the Coriolis effect, and you begin to understand why tides can be so varied. Some coastlines amplify tides through a phenomenon called resonance. It's like pushing someone on a swing. If you time your pushes just right, matching the swing's natural frequency, each push builds on the last, and soon the person is soaring high. Similarly, if the timing of incoming tidal waves matches the natural sloshing frequency of a bay or gulf, the tides can become dramatically amplified. This is why the Bay of Fundy sees such extreme tides. Its shape and depth create perfect resonance conditions. Meanwhile, inland seas like the Baltic or the Mediterranean, cut off from the main ocean's tidal rhythms, experience minimal tidal variation. But wherever you are, tides are an ever-present hum beneath the surface of life. They regulate ecosystems, they influence weather patterns, they've shaped the migration routes of animals and the settlement patterns of humans throughout history. And the best part? They're predictable. We can chart them years, even centuries, in advance. Not many things in life are so reliable. Ancient tide tables carved in stone by Babylonian astronomers still accurately predict tidal patterns today. While everything else feels chaotic, stock markets, weather systems, human relationships, the sea still follows the moon twice a day, every day, like clockwork. Or perhaps more like a lullaby, repeated softly across the ages, a reminder that beneath all the chaos of modern life, some rhythms remain constant, dependable, eternal. Gravity's invisible hand, if you sat very still, so still you could feel your heartbeat, you might sense something always happening around you, something constant and invisible. Gravity, it's the quiet force tethering you to the ground, holding oceans in place, keeping the moon dancing around us like a curious sibling. It's always there, even when you're tucked under blankets, sipping tea, or brushing your teeth in the foggy morning glow. Let's start with basics. Gravity is the attractive force between any two objects with mass. The more mass, the stronger the pull. You and I technically have gravity, though unless you're secretly made of neutron star material, you probably haven't had planets orbiting you lately. Earth, however, has tremendous mass, enough to pull us to its surface and keep the moon in orbit. Isaac Newton, the original apple-falling understander, first described gravity in the 1600s. He realized the same force pulling an apple to the ground was keeping the moon from flying off into darkness. Earth pulls on the moon. But here's the twist. The moon pulls back. Not on the whole Earth equally, but especially on the oceans, which, being liquid, are more agreeable about moving around. It's a slow-motion tug-of-war. The moon doesn't yank, it coaxes. It says, "Come here just a little," and the ocean listens. Result? A bulge of ocean water on the side facing the moon. That's one high tide. But that far side bulge? This is where gravity gets sneaky. While the moon pulls the nearest water hardest, it also pulls Earth itself, rock, mountains, and all. Just a bit less hard than the near side water. The far side water barely feels the moon's tug at all. So relatively speaking, it lags behind. Earth's mass shifts toward the moon, and the far side water seems to stretch away. Voila, a second bulge. It's not being pulled outward so much as left behind in the moon's slow embrace. This concept, differential gravity or tidal force, is one of the most quietly elegant features of our physical universe. It's not just gravity pulling everything in uniformly. It's gravity pulling different things differently. That subtle imbalance sculpts the tides way Earth's pirouette. The spinning dance Earth spins. While the moon orbits us roughly once every 27.3 days, Earth completes a full rotation in just under 24 hours. From our perspective, it seems like the moon glides across the sky daily. But in reality, we're rotating beneath that gravitational pull. As different parts of Earth pass under the two tidal bulges, one facing the moon, one opposite, we experience high tides. Between those bulges, water levels drop and we get low tides. It's a graceful planet-wide pirouette that never stops. You might wonder, if gravity is so strong, why aren't oceans simply flinging themselves at the moon? Why no dramatic sloshing or waves leaping into space? The answer is balance. The force pulling water toward the moon meets Earth's own gravity, anchoring oceans in place. The entire Earth-Moon system is held together in stable, harmonious orbit by the laws of motion Newton figured out while presumably dodging apples. There's also centrifugal force at play. As Earth and Moon revolve around their shared center of mass, not Earth's center, but a point slightly beneath its surface, this rotation creates a slight outward force. This helps create the bulge on Earth's far side, balancing the moon's pull. Result: two high tides, even though there's only one moon. Gravity isn't just playing games with water, it's subtly deforming Earth itself. The solid ground beneath your feet actually rises and falls by a few centimeters due to these gravitational forces. It's called Earth tide. While it won't flip your coffee table, it's a reminder that nothing on our planet is truly still. The sun joins the performance. The moon's role is central, but it's not the only actor. The sun also exerts gravitational force on Earth. Though nearly 400 times farther away than the moon, it's vastly more massive. Its gravitational influence is about half as strong as the moon's when it comes to tides. When sun, moon, and Earth align during full and new moons, their combined pull creates higher high tides and lower low tides. These are called spring tides, not because of the season, but because water springs farther than usual. When sun and moon are at right angles, their gravitational forces partially cancel out, leading to neap tides, more moderate and subdued. So yes, the sun is involved, but the moon, with its closeness and subtle persuasion, remains the tide's main conductor. Why two tides per day? The mystery solved: the moon pulls the ocean toward it, so you'd expect one high tide a day, right? One big, watery bulge following the moon like a loyal sea dog. Logical, tidy, satisfying. Yet reality has different plans. Most places on Earth get two high tides every day, one when the moon is overhead, and another about 12 hours later when it's on the other side of the planet. At first glance, it sounds like the moon is somehow pulling both sides at once, which seems like cheating. But this is where physics slips on its moon glasses and does something elegantly weird. Earth is not perfectly rigid. Our planet, particularly its oceans, behaves more like a squishy, spinning, sloshing sphere. When the moon's gravitational pull reaches us, it doesn't tug evenly. Water on the side closest to the moon gets pulled more strongly than Earth's center. Meanwhile, Earth's solid mass gets pulled more strongly than the ocean on the far side. This uneven pulling, differential force is at the heart of the tidal mystery. It's not that the moon is stretching oceans like taffy. It's that different parts of Earth are falling toward the moon at different rates. Result: water on the near side rushes toward the moon. Earth's body shifts a little toward the moon too. And water on the far side is left behind, forming a second bulge. Imagine holding a giant water balloon and spinning in a circle. The water inside would slosh and stretch in weird ways, not because you're squashing it, but because of movement and forces acting on it. That's Earth sloshing gently, obediently under the moon's steady gaze. The lunar day. Why tides are always late. If tides are caused by two bulges and Earth rotates once every 24 hours, shouldn't each high tide come exactly 12 hours apart? In theory, yes. In practice, not quite. Tides don't run on Earth's clock. They follow the moon's schedule. The moon orbits Earth in the same direction Earth spins, completing one orbit about every 27.3 days. This means as Earth spins, it has to turn just a little more each day to catch up with the moon. On average, it takes about 24 hours and 50 minutes for a spot on Earth to rotate back to the same position relative to the moon. That's called a lunar day. So each high tide arrives about 12 hours and 25 minutes apart. Not 12 hours. That's why, if you're vacationing by the sea, you'll notice high tide is a little later each day. The moon is constantly slipping away, fashionably late as always. Geography's wild card. How coasts shape tides. Not all coastlines play along the same way. If we lived on a perfectly smooth, water-covered Earth with no continents, tides would be simple and fairly symmetrical. But we don't live on a perfect water world. We have coastlines, bays, islands, ocean ridges, and seafloor trenches, and all of these shape how ocean water moves. In some places, like North America's East Coast, tides follow a semidiurnal pattern: two high tides and two low tides each lunar day, each high tide roughly the same height. Elsewhere, like parts of the Gulf of Mexico, you find a diurnal pattern, only one high and one low tide each lunar day. In still other areas, tides are mixed, two highs and two lows per day, but of unequal size. The ocean, it seems, enjoys improvisation. Local geography plays a huge role. Narrow bays can amplify tidal range as water is funneled into smaller spaces. This makes the Bay of Fundy in Canada a tidal superstar, with high tides reaching over 16 meters, 53 feet. In contrast, the Mediterranean Sea, almost landlocked, has barely noticeable tides at all. It's like the ocean trying to tap its foot inside a tight shoe. Then there are amphidromic points, places in the ocean where the tide hardly changes at all. These are the quiet eyes of rotating tidal systems, where water doesn't slosh up and down so much as swirl gently in a circle. If you floated over one, you might not even notice the tide was there. It's like standing perfectly still in the middle of a merry-go-round. When continents get in the way, Earth isn't a perfect sphere either. It's slightly flattened at the poles and bulged at the equator. That means gravity varies slightly across the globe, further tweaking tidal behavior. Oceans aren't shallow puddles. They're vast, deep, and varied. The Pacific Ocean alone is over 10,000 meters deep in places. Unlike bathtubs, it has underwater ridges, canyons, plateaus, and trenches, all shaping how tidal waves move. Yes, tidal waves, but not like the ones that crash dramatically on beaches. Tides are better described as planet-sized waves, very long, very slow-moving bulges of water that travel around the globe. These waves don't move at breakneck speeds, but they have enormous wavelengths, sometimes over 12,000 meters long. When they hit constraints, land, coastlines, peninsulas, islands, they bend, reflect, and sometimes get squeezed, magnified, or dampened. This is why tidal behavior varies so wildly worldwide. Take the Bay of Fundy again. Its narrow, funnel-shaped channels tidal energy into a confined area, amplifying the wave in a process like a child sloshing water in a bathtub. The shape matches the timing of the tidal wave so precisely that water resonates, piling higher with each cycle, like pushing a swing at just the right moment. It's ocean physics with perfect rhythm. On the flip side, consider the Mediterranean. Nearly enclosed by land and connected to the Atlantic only by the narrow Strait of Gibraltar, this bottleneck severely restricts tidal energy flow into the Mediterranean. So tides, there are minimal, often just a few centimeters. Walking along the shore in Nice or Naples, you might not even notice them. The Coriolis effect. When tides start spinning, tidal waves are also influenced by the Coriolis effect, the same phenomenon that makes storms spin. As Earth rotates, moving fluids like air and water are deflected to the right in the northern hemisphere and left in the southern hemisphere. This deflection helps give tidal waves their circular, whirlpool-like movement around amphidromic points. The whole system spins like a lazy water wheel, powered not by gears but by gravity and Earth's spin. And then there's resonance. Just like musical instruments vibrate at specific frequencies, so do bodies of water. Some coastal regions are tuned to the frequency of tidal forces. If the timing of the incoming tide matches the natural sloshing period of a bay or inlet, you get resonance, a condition that amplifies tidal range. It's like striking just the right note on a piano string and watching it hum to life. This is another reason why some areas see dramatic tides while others barely flutter. Tides through time. A billion-year romance. The moon has always been a loyal companion, circling us in silence, glowing with borrowed sunlight, tugging at our oceans like a patient choreographer. But the relationship hasn't always been what it is today. Like all long-term partnerships, Earth and Moon have changed each other over time. To understand how tides have changed, we need to rewind billions of years, back to when Earth was newly formed and the Moon had just been born. likely from debris of a massive collision between young Earth and a Mars-sized object named Theia. The moon emerged from that chaos glowing red-hot and orbiting much closer to Earth than now, about 22,000 kilometers away compared to today's 384,000. With the moon so close, tides would have been far more extreme. Gravitational pull on our oceans was significantly stronger, resulting in tidal bulges much larger than today's. Early Earth might have seen tides hundreds of meters high, sloshing in and out with such force that coastlines reshaped themselves daily. The ocean wouldn't have calmly risen and fallen. It would have surged and roared. Earth's rapid rotation back then added to the drama. A day on early Earth may have lasted only 5 or 6 hours. The faster the spin, the more frequently different regions passed through those massive tidal bulges. Imagine experiencing the full high to low tide cycle multiple times in a single day, a planet racing beneath a moon that loomed much larger in the sky. The Great Slowdown, how tides change the world but nature seeks balance. Over time, tidal friction caused by those surging waters began acting like a cosmic brake. Every time oceans bulged and Earth spun beneath them, friction between moving water and the ocean floor sapped a tiny bit of energy from Earth's rotation. That lost energy didn't vanish. It was transferred to the moon, giving it a boost in its orbit. As a result, the moon began slowly drifting away from Earth. It's still drifting, by the way. Today, the moon moves away at about 3.8 centimeters per year, really the speed your fingernails grow. Not exactly racing off into space, but over millions of years, it adds up. The moon's increased distance weakens its gravitational influence on our oceans, gradually making tides smaller and more subdued. Meanwhile, Earth's rotation has been slowing. Our 24-hour day is relatively recent in geological terms. Hundreds of millions of years ago, a day was closer to 22 hours. If you could fast forward a few 100 million years into the future, days might be 26 or even 28 hours long. It's a trade-off. As the moon drifts, Earth slows. Tides become more relaxed, less dramatic, more like the gentle rise and fall we know today. And yet, these changes are imperceptible within a human lifetime. You could sit by the sea every evening for 100 years and never notice the moon's slow departure or Earth's subtle deceleration. But the record is written in stone, literally. Ancient tidal patterns are preserved in sedimentary rock. In places like the Bay of Fundy and parts of Australia, fossilized ripple marks and layered mud tell scientists how often tides came in and how strong they were. Some rock layers from over 600 million years ago show 400 or more daily layers per year, compared to the 365 we experience now. This suggests days were shorter and years were longer because Earth was spinning faster. These time-stamped sediments, along with coral growth rings and other geological clues, allow us to piece together the history of Earth's rotation and the moon's retreat. It's like reading a very slow, very patient diary written by the planet itself. Tides and life, the ocean's living clock. As the tide rolls in, it brings more than just seawater. It brings life. It lifts, feeds, and carries countless creatures in a rhythm older than bones. The moon may move the oceans, but the tides move ecosystems. Let's start where land meets sea. The intertidal zone. This strip of coastline is covered by ocean at high tide and exposed to air at low tide. It's a place of dual identities, half land, half sea, changing its nature completely twice a day. For organisms living there, life is all about timing, patience, and the ability to cling really well to rocks. Take the common sea star. To us, it might look like a passive ornament of the seafloor, but it's actually a slow-motion predator. As the tide rises, the sea star ventures out searching for mussels and clams, prying open their shells with methodical, hydraulic-powered grip. When the tide retreats, it clings to a rock or burrows into damp sand to wait for the next wave. This rhythm, feed, retreat, rest, repeat, is choreographed by the tides. Or consider the humble periwinkle snail, which spends its days glued to rock surfaces, sheltering from predators and the drying sun when the tide is out. Its shells acts as a portable moisture chamber, keeping it alive during the hours of exposure. As water returns, it reactivates like a wind-up toy, sliding across wet surfaces in search of algae to graze. These tiny mollusks can be found in such dense numbers that a single square meter of rock might host hundreds of them, all waiting patiently for the sea's return. Barnacles are perhaps the intertidal zone's most dedicated residents. These small crustaceans spend their adult lives cemented headfirst to rocks, extending feathery legs to filter food from the water when submerged. When exposed to air, they seal their shells tight, creating a humid chamber that keeps them alive until the tide returns. They can survive in this dormant state for hours, even days if necessary, in one of nature's most elegant examples of biological patience. Then there are the sea anemones, flower-like creatures that bloom when underwater, their tentacles waving gently in the current, waiting to snare small fish or shrimp. When the tide recedes, they retract into gelatinous blobs, conserving moisture and energy until they can bloom again. It's a transformation as dramatic as any butterfly emerging from a chrysalis, except it happens twice daily, every day, for years on end. Entire micro-civilizations of crabs, shrimp, sea cucumbers, urchins, seaweeds, and sponges live this tidal lifestyle, each with its own strategy for staying moist, fed, and uneaten. The intertidal zone is layered like a cake, with different species occupying different heights based on their tolerance for exposure. At the highest levels, where waves only reach during spring tides, you find hardy species like certain limpets and lichens. Lower down, where submersion is more frequent, you find more delicate organisms, soft corals, nudibranchs, and fish that hide in tide pools. Speaking of tide pools, these are perhaps the most magical features of the intertidal zone. When the tide recedes, rocky depressions retain seawater, creating miniature ecosystems that function as self-contained aquariums. A single tide pool might host dozens of species: hermit crabs scuttling between shells, sea urchins grinding algae with their complex jaw structures, small fish darting between rocks, and perhaps a tiny octopus tucked into a crevice, watching everything with alien intelligence. Children who explore tide pools often have their first real encounter with marine biodiversity, poking sea anemones to watch them contract, marveling at starfish in purple and orange, discovering that those rocks are actually living creatures. It's a gateway to scientific curiosity, powered entirely by the moon's pull. Or consider the humble periwinkle snail, which spends its days glued to rock surfaces, sheltering from predators and the drying sun when the tide is out. As water returns, it reactivates, sliding across wet surfaces in search of algae to graze. Entire microcivilizations of barnacles, crabs, anemones, seaweeds, and sponges live this tidal lifestyle, each with its own strategy for staying moist, fed, and uneaten. Some organisms go even further, syncing their entire biological clocks to the tide cycle. Take the grunion, a silvery fish native to California and Mexico coasts. During specific nights of spring tides, when water reaches its highest mark, grunion swim ashore, flopping out of waves in great numbers. They lay eggs in wet sand just beyond the usual tide's reach. The eggs remain hidden and safe until the next spring tide arrives 2 weeks later, when washing over the beach again and hatching them in a frothy, silvery celebration. It's one of the few natural events that makes you say, wait, fish that go on to land to lay eggs voluntarily? Then there's the horseshoe crab, a creature that looks like it wandered out of the Cambrian period and forgot to update its wardrobe. Every year around May and June, these ancient arthropods gather en masse on Atlantic coast beaches to spawn, timing their appearance with full or new moon tides. These synchronized events are so predictable that migratory birds like the red knot have evolved to plan epic journeys around them. As crabs lay millions of nutrient-rich eggs, birds descend from the skies to refuel, gulping down crab caviar by the beakful before continuing their trek to the Arctic. Tides are nature's conveyor belt, especially for nutrients. As water moves in and out of estuaries and salt marshes, it carries organic material, microscopic plankton, and dissolved minerals. This makes tidal zones incredibly productive. Dense, rich soup kitchens for marine and bird life. Salt marsh grasses, which tolerate salty water that would kill most plants, grow tall and thick in these regions, helping trap sediment and stabilize coastlines. Human life by the tides. It's not just animals and plants that respond to tides. Whole human civilizations have lived and died by the sea's movements. Ancient communities built fish traps in the intertidal zone, cleaver rock arrangements that let fish swim in with the tide and become stranded when water ebbed. In Scotland's Orkney Islands, some of these traps are still visible today, worn by centuries of tide and time. On a more domestic scale, many fishing cultures have learned to track tides like a second clock. In Southeast Asia and Pacific Islands, entire villages structure daily routines around tidal flows. Boat trips, harvests, shoreline foraging all depend on knowing when the tide will rise and fall. In parts of Northern Europe, where mud flats stretch for miles, people still walk or drive across exposed seafloor during low tide to reach islands that disappear at high water. It's a peculiar sight, cars driving along what appears to be the ocean, only for that road to vanish under waves hours later. Even coral reefs feel the tides. Many shallow reefs rely on the ebb and flow to bring oxygenated water to their inhabitants. Tides help regulate temperature and salinity. During low tide, some reef creatures take refuge in tide pools, small, self-contained ecosystems brimming with color and mystery. A single pool might host sea urchins, clownfish, and bright purple algae, all trapped together like reluctant roommates waiting for the next splash of freedom. And then there are mangroves, those bristly, salt-loving trees that grow in tidal zones from Florida to Bangladesh. Their tangled roots provide safe havens for juvenile fish, protect against storm surges, and trap carbon more efficiently than many forests. Without tides, mangroves wouldn't thrive. And without mangroves, many coastal communities would be far more vulnerable to erosion and flooding. Tides around the world. A global tour tides may be universal, but how they express themselves around the world is anything but uniform. Like regional dialects in a shared language, tides vary wildly depending on where you are. Asterisk Bay of Fundy, Canada, the world champion of tides. Water levels can rise and fall over 16 meters, 53 feet, more than a five-story building. The bay's shape and depth create perfect conditions for resonance, amplifying tidal waves like a perfectly timed push on a swing. Visitors can walk on the seafloor during low tide, weaving between towering rock formations, only to return hours later and find those same rocks half submerged. The transition is so fast and dramatic that warning signs are everywhere. Please return to shore before the tide returns, asterisk Mont Saint-Michel, France. This medieval abbey sits on a rocky island off Normandy's coast, connected to the mainland by a causeway. During low tide, you can walk to it across the sand. During high tide, the sea surrounds it completely, turning it into a fairy tale island fortress. Tides here can rush in at the speed of a galloping horse, fast enough to sweep away the unwary. Pilgrims and tourists have been caught off guard for centuries. Severn Estuary, UK, home to the famous Severn Bore, a rare phenomenon where the incoming tide forms a wave that travels up a river against the current, sometimes stretching for miles. Surfers, kayakers, and brave swimmers gather to ride this single, long, curling wave as it rushes inland. It's a tidal roller coaster powered by gravitational clockwork. Mediterranean Sea, almost entirely enclosed by land with only the narrow Strait of Gibraltar connecting it to the Atlantic. This limited access bottlenecks tidal flow. Result: a tidal range of just a few centimeters in many places. If you weren't paying attention, you might never notice the tide happening at all. Kimberley Coast, Western Australia. Some of the most powerful and unpredictable tides on the planet. Tides can rise and fall by more than 10 meters. In narrow coastal inlets like horizontal falls, this movement creates something resembling a whitewater river. Except it's not a river. It's the ocean squeezing through two narrow gaps in cliffs at such speed it churns into raging rapids. Venice, Italy. The tidal cycle is known as acqua alta or high water. During certain times of year, especially autumn, high tides combine with winds and atmospheric pressure to flood city streets and squares. Locals walk on raised platforms. Shopkeepers stack sandbags in doorways. While these floods have always been part of Venetian life, rising sea levels and extreme weather are making them more frequent and severe. The Maldives. These low-lying atolls sit just a few meters above sea level. The difference between high and low tide can mean the difference between dry land and encroaching water. Inhabitants pay close attention to the moon and its movements, not out of curiosity, but necessity. Their homes, roads, and livelihoods are intimately tied to the ocean's moods. Harnessing the tide, the promise of tidal power every day, twice a day, tides lift and lower vast quantities of seawater across the globe, trillions of tons of it, gliding in and out like a breathing planet. All this movement contains tremendous energy, and for as long as humans have watched the sea come and go, we've wondered, could we use this? The short answer is yes, and in some places we do. Tidal power, also called tidal energy, is one of the oldest forms of renewable energy we've tried to harness. It's predictable, clean, and endlessly recurring. Tides won't forget to show up, no matter how cloudy the day or still the air. Unlike fossil fuels, they don't run out or pollute the atmosphere. They just keep rolling in. It's ancient wisdom, tidal mills. The idea of harnessing tidal energy isn't new. Way back before wires and turbines and even steam engines, ancient societies in Europe and the Middle East built simple tidal mills, structures that trapped incoming seawater in a pond or basin as the tide rose. When the tide went out, trapped water was released through a water wheel, turning millstones to grind grain. It was coastal ingenuity at its finest, using the moon's pull to make bread. One of the oldest surviving examples is the Nendrum Monastery tidal mill in Northern Ireland, dating back to the 7th century. Imagine medieval monks timing their work to the tides, watching water levels, waiting for that perfect moment when the ebbing sea could power their mill. It wasn't flashy, but it worked, using the daily rhythm of the ocean to help feed their community. A divine union of celestial mechanics and practical food production. Similar tidal mills dotted coastlines from Spain to China. Some operated continuously for centuries. The last commercial tidal mill in Britain didn't close until the mid-1900s. These humble structures proved that tidal energy was viable, predictable, and remarkably reliable. Qualities we still seek in energy sources today. Say modern approaches. 3 strategies fast forward to today, and the principles haven't changed much, just the scale, sophistication, and technology. Modern tidal energy comes in 3 main flavors. 1. Tidal barrages. The dam approach. Imagine a massive dam stretched across a tidal estuary like a giant wall with gates. As the tide comes in, Water builds up behind the dam, filling a large reservoir. When the tide turns and begins to fall, that stored water is released through turbines built into the barrage, generating electricity as it flows back out to sea. The turbines spin, generators hum, and power flows into the grid, all thanks to the moon's gravitational pull. One of the best-known examples is the Rance tidal power station in Brittany, France. Built in 1966, it was the world's first large-scale tidal power plant and remains one of the largest. Stretching 750 meters across the Rance River estuary, it produces enough electricity to power around 130,000 homes. For over half a century, it's been quietly converting tidal energy into electrical power, proving the concept works on an industrial scale. The Rance station operates on a simple but elegant cycle. As the tide rises, gates in the barrage remain open, allowing water to flow freely into the estuary. Near high tide, the gates close, trapping the water inside. Then, as the ocean outside begins to ebb, water is released through the turbines. The difference in water level between the estuary and the sea, drives the turbines just like water falling over a dam. Some tidal barrages can even generate power in both directions, when the tide comes in and when it goes out. This bidirectional generation doubles the potential energy capture, making the most of each tidal cycle. Asterisk 2. Tidal stream generators, underwater wind farms. These are essentially underwater wind turbines. Instead of air, these sleek machines are spun by ocean currents generated by tides. They're placed on the seabed in fast-moving tidal channels, like underwater highways of rushing water. As the tide flows in and out, turbines spin, generators turn, and power is produced. Because water is about 800 times denser than air, even slow-moving tidal currents pack a powerful punch. A tidal stream moving at just a few knots contains far more kinetic energy than wind moving at the same speed. This means tidal stream turbines can be much smaller than wind turbines while generating comparable power. These systems have elegant simplicity. They don't require massive dams or large-scale civil engineering projects. They sit quietly beneath the surface, almost invisible from shore, turning with the tide like windmills in a submerged field. Fish can swim around them. Boats can pass over them. They're remarkably unobtrusive. Scotland has been a leader in tidal stream technology. The Pentland Firth, the narrow strait separating the Scottish mainland from the Orkney Islands, experiences some of the fastest tidal currents in the world, up to 16 knots in some places. Several companies have deployed experimental turbines there, testing designs and gathering data. Early results are promising, suggesting that arrays of tidal stream turbines could one day provide significant portions of Scotland's electricity. Asterisk 3. Tidal lagoons. Artificial tidal basins. Tidal lagoons are a newer concept. Artificial enclosures built along coastlines, creating a protected area where water can be trapped and released through turbines. Unlike barrages, which block entire estuaries, lagoons can be constructed in locations specifically chosen for optimal tidal range and minimal environmental impact. The lagoon typically consists of a large circular or U-shaped wall built offshore, creating a substantial basin. Turbines are installed in gaps in the wall. As the tide rises outside the lagoon, water flows in through the turbines, spinning them in one direction. As the tide falls, water flows back out, spinning them in the other direction. Like tidal barrages, lagoons can generate power on both the flood and ebb tides. One proposed project, the Swansea Bay Tidal Lagoon in Wales, would have been the world's first tidal lagoon power plant. Though the project was ultimately not approved due to cost concerns, it sparked global interest in the concept. Proponents argued that tidal lagoons could provide clean, predictable power for over 120 years, far longer than most power stations, while also creating protected harbors and recreational areas. The challenge is, why aren't tides powering the world? Despite the promise, tidal energy provides less than 1% of the world's renewable energy. Why? Several significant challenges remain. Asterisk, the ocean is brutal. Building anything in salt water is tough. The marine environment is harsh and corrosive. Salt water corrodes metal. Marine organisms colonize every surface: barnacles, mussels, algae, adding weight and drag. Equipment must withstand powerful currents, severe storms, and the relentless pounding of waves. Maintenance is expensive and difficult, often requiring specialized ships and underwater divers or robots. Asterisk, geography is limiting. Only certain places on Earth have tides strong enough and fast enough to make tidal energy economically worthwhile. You need narrow straits or deep estuaries with large tidal ranges, ideally 5 meters or more, and fast-flowing water. Globally, only a few dozen locations meet these criteria. This means tidal energy can't be deployed everywhere, unlike solar or wind. Asterisk. High upfront costs. Building tidal barrages or deploying arrays of tidal stream turbines requires massive capital investment. The Rance Tidal Power Station cost millions in 1960s currency. Modern projects can run into the billions, while operating costs are relatively low. The fuel is free. After all, the initial expense can be prohibitive. Asterisk, environmental concerns. Barrages can significantly affect local ecosystems. Blocking an estuary changes water flow, which can alter salinity levels, affect sediment deposition, and disrupt fish migration routes. Species that rely on the natural ebb and flow, like salmon returning to spawning grounds, may struggle to navigate through or around the structure. Even tidal stream turbines, despite being less intrusive, raise questions. Will marine mammals collide with spinning blades? How will the devices affect seafloor habitats? While studies suggest impacts can be minimized through careful siting and design, more research is needed. The promise. A tidal future? Still, the idea of drawing clean, rhythmic power from the moon's pull is deeply appealing. It's almost romantic. Energy from a celestial body 384,000 kilometers away, channeled through the oceans and into our homes, our schools, our hospitals. And tidal power has genuine, substantial advantages over other renewables. Asterisk, perfect predictability. Unlike solar and wind, tidal power is almost perfectly predictable. We can forecast the tides decades, even centuries in advance with extraordinary precision. Grid operators dream of this kind of reliability. They can plan exactly when tidal plants will generate power and how much, making it easier to integrate into electrical grids and balance supply with demand. Asterisk, energy density. Water carries far more energy than air per unit volume. This means tidal installations can be smaller and more compact than comparable wind farms while producing similar amounts of power. Asterisk, longevity. Tidal installations can last for many decades. The Rance station has been operating reliably for over 50 years with regular maintenance. That's a long operational lifespan compared to many power generation technologies. Asterisk, no fuel costs. The fuel, the moon's gravitational pull transmitted through ocean tides, is absolutely free and will continue as long as the moon orbits Earth. No price fluctuations, no supply chain disruptions, no geopolitical conflicts over resources. In the coming decades, as the world shifts more urgently toward renewable energy to combat climate change, tidal power may play an increasingly important role, especially in coastal nations with suitable geography. Innovations in materials science could produce more corrosion-resistant components. Advances in marine robotics could make underwater maintenance cheaper and safer. New turbine designs could extract more energy more efficiently while posing less risk to marine life. Perhaps one day, the sea itself will help power the lights in your kitchen, charge the bus you ride to work, or keep the hospital running during the night. quiet, clean energy drawn from an ancient rhythm that's been moving invisibly beneath the surface since the moon and Earth first found each other in the darkness of space. And somewhere far above, the moon will continue its patient orbit, pulling at the oceans, indifferent to whether we harness its power or simply watch the waves roll in and out, as humans have done for millennia. Set ancient beginnings way back, before wires and turbines and even steam engines, ancient societies in Europe and the Middle East built simple tidal mills, structures that trapped incoming seawater in a pond or basin as the tide rose. When the tide went out, trapped water was released through a water wheel, turning millstones to grind grain. One of the oldest surviving examples is the Nendrum Monastery tidal mill in Northern Ireland, dating back to the 7th century. It wasn't flashy, but it worked, using the daily rhythm of the ocean to help monks make flour. A divine union of celestial mechanics and snack preparation. Modern tidal energy fast forward to today, and the principles haven't changed much, just the scale and technology. Modern tidal energy comes in a few flavors. Asterisk tidal barrages. Imagine a dam stretched across a tidal estuary like a giant wall with gates. As the tide comes in, water builds up behind the dam. When the tide turns and begins to fall, that water is released through turbines, generating electricity as it flows back out to sea. One of the best known examples is the asterisk Rance Tidal Power Station in Brittany, France, built in 1966. It's still operating today and produces enough electricity to power around 130,000 homes. Asterisk tidal stream generators, essentially underwater wind turbines. Instead of air, these sleek machines are spun by ocean currents generated by tides. They're placed on the seabed in fast-moving tidal channels, like underwater highways of water. As the tide flows in and out, turbines spin, generating power. Because water is about 800 times denser than air, even slow-moving tidal currents can pack a punch. These systems have elegant simplicity. They don't require dams or large-scale infrastructure. They sit quietly beneath the surface, turning with the tide like windmills in a submerged field. Tidal lagoons, artificial enclosures built along coastlines. Water flows in and out of the lagoon through turbines, much like with a barrage, but the lagoon can be constructed in places where building a dam across an estuary isn't feasible. The challenge is, despite the promise, tidal energy is still relatively rare. Why? The ocean may be predictable, but it's not user-friendly. Building things in salt water is tough. The environment is harsh and corrosive. Marine equipment must withstand strong currents, storms, and barnacles with dreams of permanent residency. Maintenance costs can be high, and installation isn't cheap. Then there's the geography problem. Only certain places on Earth have tides strong enough to make tidal energy worthwhile. You need narrow straits or deep estuaries with large tidal ranges and fast-flowing water. That's why only a handful of locations, like parts of the UK, Canada, and South Korea, are seriously investing in this technology. There are also environmental concerns. Barrages can affect fish migration, sediment flow, and local ecosystems. Changing the natural flow of tides might alter salinity in estuaries or disrupt habitats that depend on the usual ebb and flow. The promise still, the idea of drawing clean, rhythmic power from the moon's pull is deeply appealing. It's almost romantic, energy from a celestial body, channeled through the sea and into our homes. And tidal power has big advantages. Unlike solar and wind, it's almost perfectly predictable. We can forecast tides centuries in advance. That kind of reliability makes it easier to integrate into power grids and plan around. The moon, after all, is not known for being spontaneous. In the coming decades, as the world shifts more seriously toward renewable energy, tidal power may play a growing role, especially in coastal regions where infrastructure can be tailored to local conditions. Innovations in design, materials, and deployment could make underwater turbines cheaper, more efficient, and friendlier to marine environments. Perhaps one day, the sea itself will help power the lights in your kitchen, the train into town, or even the phone you're listening to this on. A quiet energy drawn from an ancient rhythm, moving invisibly beneath the surface. The moon's quiet influence. More than just tides each night, as the moon glows quietly above, something extraordinary happens across the surface of our planet. It doesn't roar, it doesn't flash, but it moves mountains of water, literally. This gentle, predictable force is not just a curiosity or a convenience. It's a fundamental part of how Earth works. The tides are more than water levels shifting. They are a conversation between Earth and Moon, a soft, endless dialogue in gravity's language. You could think of tides as Earth's response to the Moon's gravity. The Moon pulls and the oceans lean in. It's not a tug exactly, not like yanking a rope, but more like a slow beckoning, a celestial invitation that the seas have been answering for over 4 billion years. And Earth listens in kind. It responds not just with water, but with motion, with balance, with time itself. Because tides don't only affect coastlines, they influence everything from animal behavior to planetary stability. At the heart of it all is the moon, quietly keeping rhythm. Let's appreciate what a remarkable partner the moon has been. Unlike the sun, which roars with radiation and flares, the moon says very little. It reflects rather than emits. It drifts rather than burns. And yet, it's the moon that shapes the daily ebb and flow of the oceans. It does so with relentless consistency, making the same request of Earth every day. Come closer, then let go. That request creates tidal bulges. But what's especially fascinating is that those bulges aren't perfectly aligned with the moon. Because of Earth's rotation, the ocean bulges lag just slightly ahead of the moon's position in the sky. That tiny misalignment creates a torque, a twisting force that pulls the moon forward in its orbit and simultaneously slows Earth's rotation. It's like Earth is giving the moon a little push, saying, "Here, take a bit more momentum." And the moon goes inching farther away, about 3.8 centimeters every year. As it does, Earth's day lengthens ever so gradually. In a few 100 million years, a single Earth day might last more than 25 hours. This mutual exchange is called tidal locking in progress. Eventually, billions of years from now, the moon might become so distant and Earth spins so slow that the same side of Earth always faces the moon. Just as the moon already shows only one face to us. The gravitational conversation would then settle into a quiet, almost frozen pose, a final embrace. But we are nowhere near that moment now. Instead, we live in the golden age of tides, where the moon still circles us, Earth still turns, and the oceans still breathe twice a day. The moon as Earth's stabilizer. This rhythm governs so much more than shorelines. Tides influence climate. They help distribute heat and nutrients through ocean layers, driving large-scale currents and keeping marine ecosystems oxygenated and alive. Without tides, the deep ocean might stagnate, becoming colder, less dynamic, and less hospitable to life. Tides shape migration patterns, especially for sea creatures that use the lunar cycle as a biological clock. Sea turtles often hatch during specific tidal phases to increase their survival odds. Plankton rise and fall with the tide, feeding fish that feed seabirds that feed everything else. It's a chain of life tuned to the moon. Even human cultures, our calendars, our myths, our sense of time have grown around the moon's pull. Lunar calendars guided early agriculture. Coastal cities evolved around tidal patterns. Entire languages developed poetic ways to describe the sea's rise and fall, as if recognizing the ocean's connection to something larger and more eternal. The moon has made Earth what it is. Without it, Earth's axial tilt would wobble more wildly, destabilizing seasons and climates. The moon acts like a gravitational stabilizer, keeping our planet's spin relatively steady. Without it, we might not have the regular seasons or long-term climate stability that helped life take root and thrive. The moon gives Earth its composure, its calm, and there's something comforting, perhaps even poetic, about that. That something so far away, so silent, can have such a profound, tender influence that we are connected, quite literally, to something outside our planet. We don't just orbit the sun, we dance with the moon. The endless rhythm, this gravitational relationship, though ancient, remains deeply current. Our modern world may be filled with artificial light and city hum, but the moon's rhythm still plays on. If you walk along a beach tonight or look out over a harbor, you'll see it. Boats rising slightly on their moorings, wet sand drying in rippled paths, shorebirds probing newly revealed shallows for one last snack before the tide comes in again. And maybe, just maybe, you'll feel it too, the slow pulse of the planet responding to something far away. The moon, ever the quiet partner, continues to shape the tides without fanfare. No engines, no schedules, just gravity, just presence. So if you ever feel disconnected, overwhelmed, or unmoored, consider this. Every few hours, the entire ocean rises and falls, guided by a force you cannot see, but can always count on. The moon is still out there, pulling gently on the world, and the world answers in tides, in rhythms, in whispers between moon and sea. Closing thoughts. The ocean's lullaby. And so, as we come to the end of our journey, we return to where we began. Standing at the edge of the sea, listening to the quiet rhythm of the tides. Now, perhaps you see them a little differently, not just as waves rolling in and out, but as part of a grand, ancient conversation between Earth and Moon, a gravitational duet that's been playing long before we arrived and will continue long after we're gone. We've drifted through the science, from bulging oceans and spinning Earth to moonlit fish migrations and the slow expansion of time itself. We've visited rocky shorelines and underwater turbines, seen monks grinding grain with seawater and crabs moonwalking their way to reproduction. We've learned that the moon, despite its quiet presence, is one of the most influential forces shaping our planet, and that the tide, for all its calm and repetition, is anything but simple. It's constant, but never still. Predictable, but endlessly varied. A soft-spoken force with the power to shape continents, feed ecosystems, and slow the turning of the earth. And now, dear listener, as you lie back, perhaps drowsy, perhaps already floating toward dreams, I hope the tides of this story have carried you gently to that place between wakefulness and sleep. As you drift off, think of the tides moving far away, unseen but certain. Think of the moon turning its pale face toward us, whispering across space. And think of the water rising slowly against the shore, as it has done for billions of years. It is the ocean's breath, the earth's quiet heartbeat, the moon's gentle pull, all of it part of the same ancient, elegant pattern. And it's still happening right now, even while you sleep. If you enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap subscribe for more peaceful explorations with the sleepy scientist. And before you drift off, I'd love to know, where in the world are you listening from? What time is it there? Leave a comment if you're feeling cozy enough to share. Wherever you are and whatever the hour, may your tides be calm, your moon be bright, and your dreams be pulled gently by the forces that have always moved the sea. Good night.